Calculus and polar coordinates. Let's start with the area. So before, we had area below the graph, which I will review for you here. We had X and Y, and then there was a roof, and then there was the bottom part. And I call it top and the bottom, right? It was top, that's how I call it, and the bottom. Higher and lower, bigger and smaller. There was also right minus left. And then we approximated whatever was between with rectangles. That's a very fat rectangle. With rectangles. They had the same widths, but different heights, and they were touching bottom and top, either with midpoint, left end point, right end point. Then we learned approximating with other things too. But originally they were rectangles. Infinitely made rectangles gave us perfect approximation by making them super thin and blah, blah, blah. Yeah, that's not going to work in polar. What is top and what is the bottom? Like if there's a circle, what is the top and what is the bottom of the circle? If there's a rose, which we're going to learn to do today, where is the top and where is the bottom? So this was convenient because X and Y have this idea of run and rise. Run gives you width, rise gives you height. So in 3D, we also have front and back. That's why they call rectangular coordinates, because they give you idea of the rectangle, and then objects are put in the rectangle. But polar coordinates, sometimes called spherical coordinates in 3D, because they create circle and with depths, spheres. So we're going to learn this in Calculus 3. That's why it will not work to have the same idea. What we're going to do is we're going to create the area between these types of lines, between A and B. So A and B are points. They have different radii, right? Because radius describes how far I am from the pole R1 and R2. Pole is at the center. They all have different angles, theta 1 and theta 2. Let me put it down. Usually people put it down. With the positive x-axis, theta 1 and theta 2. What is the area between those two lines? So people were thinking, okay, rectangles, if I try to, that's how it's kind of a creative process. You as an engineer, for example, or physicist major, you figure out, okay, how would I approximate with rectangle? But then it becomes like super thin here. So there is an object that will help us called a sector. A sector or a segment. The sector or segment are coming from circle. You learn it from in geometry class. If you take a center on the circle, and then you take this piece, which looks like piece of pie. If you fill it in like so now it's a piece of pizza basically. Oh, it's a strawberry pie. Oh yeah, look at that. Then this is called a sector. A sector. And the sector has a formula. Area of the sector is known. Why did we use rectangles again? Because we knew the area of each rectangle. Width times height, h times w. Well, w times h. So actually area of the sector is known as well. There's a formula for that. So why not to fill it in this object with sectors? Different sectors. The sectors have a nice curve at the very end. So that also is very helpful. It will be either overestimation or underestimation. And that's how we're doing it. We're filling in the object that was done by the rotation with sectors. Let's write it down. Here's a circle. The circle has a sector. And the sector has a radius r. That's how far it is from the center, this part away from the center. And it has a theta. The rotation around the whole thing is 2 pi. So this one is a little bit less than 2 pi. The formula A for the sector, the formula is coming from, let me zoom out. The formula is coming from pi r squared. So we're going to have this parentheses. Pi r squared is the total thing. But then theta divided by 2 pi is the part of that thing. So the piece out of the whole pi. We have a piece of pi out of the whole pi. Theta out of 2 pi. The whole rotation represents 2 pi. The whole rotation is, well, now it's confusing with different color. The whole rotation is 2 pi, while the piece we need has just theta. So theta is taken out of 2 pi, whole thing. And then if you simplify that, it gives you the formula. A is 1/2 stays, pi and pi cancels out, and it becomes theta r squared. And that's the formula of the sector. It's very, I'm almost sure you learned it before in school, just kind of don't remember. That's the formula of the sector. Area, oh, not the formula of the area of the sector. Area of the sector. 1/2 theta r squared. So we're using sectors. Rectangles versus sectors. That's the idea. Instead of rectangles, we're going to use sectors, infinitely many of them. So we're going to have area of the total thing between two curves. Will be approximately the sum of those sectors, which is the sum of all of those 1/2 r squares. The thing is, not only there will be many of them, so let's put I from 1 to n, and we're going to set n to go to infinity, just like we had with the rectangles. But also, we're going to assume that sectors will have the same angle. Where did my theta go? We're going to use a d theta. D theta or delta theta is called, they will have the same angle. The same angle. Because it's just convenient, we always do the same thing. Here's the sector number 1, here's the sector number 2, and we're going to assume that they all have the same angle. Then we can factor out the same angle. We can also send n to go to infinity, and it gives us definition of the integral. So we have limits, use limits, right? Use limits, and goes to infinity. Now we have infinitely many sectors. If we have infinitely many sectors, instead of having 3, this one, and this one, and this one, and this one, and this one, that's not 3. 1, 2, 3, 4, 5, 6. Instead of 6, we're going to have them so thin that they will cover exactly the whole area perfectly. They'll be so thin you will not see the difference between them anymore, and that becomes a perfect piece of cherry pie in this case, because it's red. And the formula is A will be, we're taking limit of n going to infinity, and then whatever I showed before is the sum of 1/2 r squared. I is from 1 to n, d theta or delta theta. Sometimes we call delta theta. Delta theta. Delta means difference, right? Small or small difference, small angle. That gives us a final formula. The integral, definition of the integral, I'm kicking out 1/2 outside. It will be integral r squared is the only thing that's left inside. Here it is. D theta. Theta is coming from alpha to beta, which I'm going to show you in a second. Let me put this in the rainbow box. It's a new formula of whatever we already learned before. Area in polar. Area between curves in polar coordinates. Are you making a box? Yes. Wow. That's unnecessary huge. Unnecessary ugly. Perfect. So that is called area between curves, area in polar coordinates. Area in polar. So area in polar is 1/2 integral from alpha to beta r squared d theta, where let me review for you, where x, that's kind of actually jumping between, I guess not necessary, where r is the distance from the pole and theta angle between the curve and the positive x-axis. So what are alpha and beta? Oh, this is what I can say, yes. Where r is given as a function of theta. Theta is the input, r is the output. That is what I wanted to say. What is alpha and beta? Check it out, I'll show you. That's actually a pretty neat way to explain. Alpha is the angle between this, don't do that, between this first curve. Go back. Alpha is the angle between this first curve and the positive x-axis. So I want to show you this. If I make a line, and then I will find the first angle, that's what we're gonna call alpha. I call it theta 1. Usually in the book they rename it as alpha, which is not necessary. And then the next angle is this one. This line creates the angle with positive x-axis. So it's gonna be the second angle, which is called beta. That is what's happening. Actually, let me draw it. And we're finding the area between those two curves. Very interesting that we basically scanning it this way. Before we were doing it with rectangles. Now we're doing it this way. We're scanning not from top to bottom like we did before. Before I was explaining, oh, we're doing it this like CAT scan. From top to bottom, from top to bottom, from top to bottom, from right to left, from right to left. Now we're doing it from curve number 1 with the angle alpha. We're scanning it with the rotation like so. We're scanning by rotating it around the clock or around the circle up until curve, second curve with the angle beta. That's what we're doing. So we're rotating now. And that's why sectors are used. So it's going to be like, and that doesn't even have to have from alpha to beta, basically, from the small angle to a bigger angle. That is good enough. But actually, sometimes I do show this idea that the rotation happens. We have curve number 1, and curve number 2. Curve number 1 creates alpha angle, curve number 2 creates beta angle. What we're looking for is for the area between those two curves. And this area looks like, let me use this color, looks like so, from alpha to beta, from alpha to beta, from alpha to beta, from first curve to the second curve. That's how we find the area. Does that make sense? What do you think? Very interesting, very unusual idea. Yes?
So, just to make sure I understand, will it always be, like, no matter what quadrant your sector's in, will it always be to the x-axis?
Yeah, exactly. That's a good question. No matter what the quadrant is, the angle, by the definition, have to be with the positive x-axis. So if it's here, then it's going to be huge. If it's here, then it's going to be huge or negative. So that actually doesn't contradict what we learned before about the angles. Yeah, either you go down to minus pi over 2, or you do 3 pi over 2. Yeah. Good question. Thank you. Let's do a couple examples.